Look up. Not now, maybe. But you know the feeling. You have stood outside on a clear night and looked up, and something in you went quiet. Something in you went quiet. Something in you recognized that the darkness above was not emptiness. It was full, crowded with old light. Crowded with distances the mind refuses to actually hold. And it felt permanent. That is the first thing to say. The night sky feels permanent. It feels like something that was there before you were born and will be there long after everything you know has ended. The stars feel fixed. The constellations feel carved. Even the word constellation suggests something that does not move, does not shift, does not lean toward you or pull away. A pattern, a given, a thing that simply is. But the sky is not permanent. It never was. The stars move. They drift across the galaxy in slow arcs that take millions of years to complete. The constellations you were taught as a child, Orion, the Big Dipper, Cassiopeia, they are not fixed shapes. They are accidents of perspective. They are what those particular stars happen to look like from this particular planet at this particular moment.
We simply do not live long enough to notice, and there is one change coming that is larger than any other. One change that will, over billions of years, remake the sky above this planet entirely. Remake the galaxy we live in. Remake the structure of the local universe in a way that nothing has remade it since our solar system was young. Right now, at this moment, while you breathe and the night is quiet and the stars look fixed in their places, another galaxy is falling toward us. It has been falling toward us for a very long time. It is called Andromeda. It is the nearest large galaxy to our own, and it is moving in our direction at roughly 110 kilometers every second. That is 246,000 miles per hour. That is fast by any human measure. Fast enough to cross the Atlantic Ocean in about 23 seconds. Fast enough that if you could somehow see it moving, you might call it urgent, but you cannot see it moving. The distances involved are so immense that the motion is invisible. Andromeda looks perfectly still. It has always looked perfectly still.
For as long as human beings have had eyes to look up with, Andromeda has appeared as nothing more than a faint smear of light in the autumn sky, a soft blur near the constellation named for the princess of the same name, and it has looked like it is just sitting there, quietly, doing nothing. It is not doing nothing. In approximately 4.5 billion years, the two galaxies will collide. They will pass through each other, and then circle back and collide again, and eventually they will merge into something new. Something neither of them is now. The Milky Way as we know it. The broad river of stars that you can see on a very dark night. The galaxy in which our sun is one unremarkable star among 200 billion others, will cease to exist as a separate thing. This is not a catastrophe. That is important to say clearly, and we will come back to it many times. It is not a catastrophe. It is a transformation. It is the kind of thing the universe does, slowly, over spans of time that make human history look like a single breath. For now, just sit with the feeling. The sky you see tonight is not the sky that will always be there. The galaxy you live inside is not the galaxy that will always be there. Something is coming. Something slow and vast and silent, and in its own way, beautiful.
And it has already begun.
Before anything else, you need to know what Andromeda is. Not in the way you might look up a fact quickly and move on. You need to sit with it for a moment, because Andromeda is one of those things that the mind can state easily and almost never truly absorbs. It is one of those facts that sounds like information and actually functions more like a doorway. You can walk through it, or you can stand in front of it and read the sign and go home. Most people read the sign. Tonight, let's try to walk through. Andromeda is a galaxy. A galaxy is not a star, and it is not a collection of stars the way a solar system is a collection of planets. A galaxy is something larger than that, something so much larger that the comparison almost fails. Our own galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. Andromeda is estimated to contain around 1 trillion, a trillion stars. Each one of them a sun, many of them larger than our sun, many of them older, many of them with planets in orbit around them, and Andromeda is 2.5 million light-years away. A light-year is the distance light travels in 1 year. Light moves at just under 300,000 kilometers per second. In a single second, light travels from the Earth to the Moon and back again, more than once.
In 8 minutes, it crosses the distance from the Earth to the Sun. In 4 years and a few months, it travels to the nearest star beyond our solar system. Light from Andromeda takes 2.5 million years to reach us. That means when you look at Andromeda, when you stand outside on a clear autumn night and find that faint smudge of light near the constellation of Andromeda, that soft blur that ancient sky watchers called a cloud or a nebula or simply a wonder, you are not seeing Andromeda as it is. You are seeing Andromeda as it was. 2.5 million years ago, before our species existed, before the ice ages carved their signatures across the continents, before the first stone tools, the light that reaches your eyes right now left Andromeda in a time when human beings were not yet human, when our ancestors were something different, something still becoming. The galaxy you see is ancient news, a message from before the world you know. Andromeda is the nearest large spiral galaxy to the Milky Way, and Andromeda both like the large and small Magellanic clouds visible from the southern hemisphere. But in terms of a full-size spiral galaxy, a galaxy comparable in structure and scale and grandeur to our own. And it is not a small neighbor. Andromeda is larger than the Milky Way, significantly larger by most measures. Its disk of stars stretches roughly 200,000 light-years across, compared to the Milky Way's estimated 100,000. If you could somehow see both galaxies from outside, hovering in intergalactic space, with a view that no human eye will ever actually have, Andromeda would appear larger. It would look like an older sibling, a senior partner. A vast, slow-turning wheel of light, with our galaxy spinning nearby, smaller, perhaps a little younger, perhaps a little less settled. Both are spiral galaxies. Both have a bright central bulge of older stars and long arms of younger stars, and dust and gas that spiral outward like the arms of a pinwheel turning in a wind that takes hundreds of millions of years to complete a single rotation. Both contain enormous structures we are still mapping, still understanding, still finding surprises in. They are, in many ways, siblings. But for most of human history, no one knew any of this. No one knew Andromeda was a galaxy. No one knew.
He noted it carefully in his book of fixed stars, described it as a nebula, something cloudy and indistinct, Not quite a star, not quite nothing. He had no way to know what it was. No instrument existed yet that would have told him. He just looked, and he recorded what he saw, and he moved on. The little cloud, 2.5 million light-years of distance compressed into those 3 words. For centuries after Al-Sufi, the blur remained classified as a nebula, a cloud of gas within our own galaxy. Something local, something belonging to the same system we lived in. The universe in most human thinking was the Milky Way. Everything visible in the sky was part of the same structure. There was no concept of other galaxies, other island universes, other systems of hundreds of billions of stars separated from us by voids so vast they redefined the word distance. That changed in the 1920s. And the person most responsible for changing it had a name that would become inseparable from the story of how we understand the universe. Edwin Hubble. Hubble was not the only person working on these questions. Science rarely works that way, with a single genius arriving from.
But Hubble had access to the largest telescope in the world at the time, the 100-inch Hooker telescope at the Mount Wilson Observatory in the mountains above Los Angeles, and he used it to see farther and more clearly than anyone had seen before. In 1923 and 1924, Hubble was studying the Andromeda Nebula. He was taking photographs. Carefully, repeatedly, over many nights, he was capturing images of that spiral of light and looking for something specific within it. He was looking for a type of star called a Cepheid variable. A Cepheid variable is a star that pulses. It brightens and dims in a regular rhythm, expanding and contracting over a period of days or weeks, and it does this with a precision that is almost musical. The period of the pulsation, how long it takes the star to go from bright to dim and back again, is directly related to the star's actual luminosity. Its true brightness, not how bright it looks from Earth, but how bright it actually is. This relationship was discovered by an astronomer named Henrietta Swan Leavitt in the early 1900s. Leavitt was employed at the Harvard College Observatory as a human computer, a person whose job was to measure and catalog stars from photographic plates. Tedious and precise work.
She noticed something in the Cepheid variables she was cataloging. The ones that pulsed more slowly were intrinsically brighter. The period of the pulse and the luminosity were linked. She published this finding. It was one of the most important astronomical discoveries of the 20th century, and for a long time it was not widely attributed to her. Hubble used Leavitt's discovery like a ruler. If you know how bright a Cepheid actually is, and you can measure how bright it appears to you, you can calculate exactly how far away it must be. Brightness falls off with distance in a precise mathematical way. A star that is twice as far away appears 4 times dimmer. A star that is 10 times as far away appears 100 times dimmer. The relationship is exact. It does not require assumptions. It does not depend on the chemistry of the star or the conditions around it. It is simple geometry applied to light. So when Hubble found a Cepheid variable in his photographs of Andromeda, when he identified a star that was pulsing in that characteristic rhythmic way, he had what he needed. He measured the period of its pulse. He used Leavitt's relationship to determine its actual brightness. He compared that to how bright it appeared in his photographs. And the number he got was staggering. The star was not.
It was far too dim for its actual brightness to make sense at the distances within our galaxy. It was much, much farther away, far enough that Andromeda itself, the entire nebula, the entire spiral of light, could not possibly be a local cloud of gas within our own system. It had to be something else entirely. It had to be a vast system of stars, separate from our own, at an enormous distance. Hubble wrote the letters VAR on his photographic plate, circling the star he had found, marking it as a variable. That plate still exists. The ink mark and the small circle around that star represent the moment the known universe expanded by a factor we had no previous way to imagine. He announced his results in January of 1925. The Andromeda Nebula was not a nebula. It was a galaxy, an island universe, a system of stars as vast as our own, utterly separate from our own, at a distance of roughly 900,000 light-years by his original calculation. The number has since been refined and corrected. We now know the distance is closer to 2.5 million light-years. But the fundamental discovery was correct and definitive and world-remaking. The universe was not the Milky Way.
Think about what that means for a moment. For centuries, human beings looked at the night sky and thought they were seeing their home, the full extent of existence, the whole of everything. And then, in 1925, someone pointed a very large telescope at a smudge of light and showed that everything we thought we knew about the size of the universe was not even approximately correct. We had been looking at a suburb and thinking it was the world. That is the thing about distance in astronomy. It keeps doing this. Every time we think we understand the scale grows. Every time we think we have found the edge, there is more. The universe is not obligated to be the size we can comfortably imagine. Andromeda, that faint smudge, that little cloud, that soft blur you can find with your naked eye on a clear, dark autumn night, if you know where to look. It is the most distant thing a human being can see without any instrument at all. No telescope, no binoculars. Just eyes. Just the same eyes.
There is a way that light changes when its source is moving. You have heard a version of this with sound. A car approaches on an empty road, and the engine sounds higher pitched than it really is. The car passes you and recedes, and the pitch drops. The sound waves in front of the moving car are bunched closer together, reaching your ears more frequently, sounding higher. The sound waves behind the car are stretched out, reaching your ears less frequently, sounding lower. This is called the Doppler effect, and it applies not only to sound, but to light. Light from a source moving toward you is shifted toward the blue end of the spectrum. The waves are compressed. The frequencies are higher. This is called a blue shift. Light from a source moving away from you is shifted toward the red end of the spectrum. The waves are stretched. The frequencies are lower. This is called a red shift. The amount of shift tells you how fast the source is moving and in which direction. In 1912, an astronomer named Vesto Melvin Slipher was working at the Lowell Observatory in Flagstaff, Arizona. Slipher was methodical, patient, careful. He was using a spectrograph attached to the observatory's telescope to split the light from various nebulae into their component wavelengths. To look at the spectral finger.
Hydrogen has its lines. Calcium has its lines. Each element leaves a signature as distinctive as a fingerprint.
When you look at the spectrum of a star or a nebula, you can identify which elements are present because their signature lines are there, right where they always are, except when they are not where they always are. Slipher looked at the spectrum of the Andromeda Nebula. He found the signature lines. He found the calcium lines, which were particularly strong and clear in his spectrographic plates, and they were not where they should have been. They were not sitting at the wavelengths that calcium always occupies when its source is stationary. They were shifted toward the blue end of the spectrum, measurably, definitively. Blue shift. Andromeda was not moving away. It was moving toward us, toward the solar system, toward Earth. The light was compressed. The waves were bunched, and Slipher could calculate the speed from the degree of the shift. The mathematics of the Doppler effect are exact enough that the velocity follows directly from the measurement, roughly 300 kilometers per second.
For years, this fact sat somewhat quietly in the literature. It was known. It was noted. But the full implications were not immediately clear because the distance to Andromeda was still uncertain and the nature of the object itself, galaxy or nebula, was still debated. Once Hubble established that Andromeda was a galaxy, and once the distance was properly measured, the blue shift took on a different weight. A galaxy, 2.5 million light-years away, moving toward us at 110 kilometers per second. The question then became, will it actually hit us? Or will it pass by at some safe angle, close but not intersecting? This is where the measurement becomes much harder. Knowing how fast something is moving directly toward you is relatively straightforward. The Doppler shift gives you that number cleanly. But knowing how fast something is moving sideways, across your field of view, is another problem entirely. The sideways motion, the tangential velocity, the component perpendicular to your line of sight, produces no Doppler shift. It does not change the wavelength of the light. You have to detect it another way. And the only way to detect it is to watch very, very carefully over a very long time and measure whether the position of the object has changed in the sky.
It exists, but it is almost impossibly small to measure. The precision required is staggering. For decades, it was beyond the reach of any instrument we had. Then came the Hubble Space Telescope, and then came Gaia. The Hubble Space Telescope, orbiting above Earth's atmosphere where there is no blurring from air currents or weather, can measure the positions of stars with a precision that ground-based telescopes cannot match. And Gaia, the European Space Agency's astrometry mission launched in 2013, is designed to do essentially one thing with extraordinary care: measure the precise positions and motions of stars. Billions of stars, with an accuracy measured in micro-arcseconds. Fractions of a fraction of a degree so small, they are essentially beyond intuitive comprehension. Using measurements from Hubble and later Gaia, astronomers have been able to detect the sideways motion of Andromeda, to tease out, from the apparent positions of stars in Andromeda observed years apart, the tiny shift that tells you how the galaxy is moving across the sky as well as toward you. What they found was important. The sideways motion is small, much smaller than the motion directly toward us. The two galaxies will collide. The calculations are not perfectly precise. The sideways motion is difficult to measure and carries some uncertainty. but the range of predictions all lead to the same conclusion. Collision is inevitable. The uncertainty is in the exact timing and the exact geometry of the encounter, not in whether it will happen. The current best estimates place the first close passage of the two galaxies at roughly 4 billion to 4.5 billion years from now. Some models suggest it could be slightly sooner. Some suggest slightly later. But within that range, the conclusion is firm. 4.5 billion years is a long time. It is longer than Earth has existed. Our planet formed roughly 4.5 billion years ago, which means the collision of Andromeda and the Milky Way is approximately as far in the future as the formation of Earth is in the past. The full lifespan of our planet, from its molten beginning to this present moment, replayed once more into the future, and somewhere at the far end of that second span of time, the galaxies meet. Let that settle. The universe operates on timescales that make patience into something else entirely.
It sounds like destruction on the largest possible scale. It sounds like something that should frighten you. It should not. And the reason it should not is one of the most beautiful things in all of astrophysics, and it has to do with the nature of space. Space is almost entirely empty. Not just somewhat empty. Unimaginably, incomprehensibly, staggeringly empty. The distances between stars, even within a dense galaxy like the Milky Way or Andromeda, are so vast that stars almost never actually touch each other during a galactic collision. They pass through, like two handfuls of sand thrown at each other in a wind. The grains almost never hit. They scatter through the space between them and land somewhere different, rearranged, but largely intact. Consider this. The nearest star to our Sun is Proxima Centauri, which is roughly 4 light-years away. Our Sun itself has a diameter of about 1.4 million kilometers. If you shrink the Sun down to the size of a grain of sand, a grain about 1 millimeter across, then on that same scale, Proxima Centauri would be 4 kilometers away. A grain of sand separated from the next grain of sand.
The stars will pass each other in the darkness, separated by distances so vast that their gravitational fields will pull them into new orbits, new trajectories, new positions. But the stars themselves will remain whole. They will be shuffled. They will be redistributed. But they will not be destroyed by the collision. This is not to say nothing dramatic happens. Something very dramatic happens. But the drama plays out differently than the word collision suggests. The gas and dust clouds that drift between the stars, the raw material from which new stars form, do interact with each other. Unlike individual stars, which are so small relative to the distances between them that they almost never meet, the gas clouds are large and diffuse, and they do collide. They compress. They heat up. And when gas clouds compress and heat under the immense gravitational forces of two galaxies pushing through each other, something happens that is almost the opposite of destruction. Stars are born. Galactic collisions trigger what astronomers call starbursts, periods of dramatically accelerated star formation when new suns ignite in numbers that dwarf the ordinary rate of stellar birth. When two galaxies of gas and stars push through each other.
There are pairs of galaxies we can see with telescopes that are currently in various stages of collision and merger. They look spectacular. They look violent, in the way a storm looks violent. powerful and beautiful, and not directed at you. Long streams of stars trail behind the interacting galaxies like tails of light. The cores of the two galaxies spiral toward each other. Regions of starburst glow intensely blue with the light of thousands of newly formed hot stars. And slowly, over hundreds of millions of years, the two galaxies lose their separate identities and become something new. We know this process. We have seen it in other parts of the universe. We can model it with computers. We can run the simulation of our own galaxy's collision with Andromeda many times over, letting the physics play out, watching the trajectories and the gravitational dynamics and the star formation rates. The simulations are not identical every time. They depend on assumptions about the exact speed and angle of approach, and some of those measurements still carry uncertainty. But they agree on the broad strokes. The galaxies will encounter each other. The first passage will not be a merging, but a close flyby.
Then they will separate again, not because they are truly moving apart, but because they are caught in each other's gravity, like two balls on a long rubber band that stretches out and then snaps back. They will come together again, perhaps more than once. And eventually, after several billion years of these encounters, the two will settle into each other, their stars mixed together, their cores drawn toward the same center, their separate identities lost. What emerges will be a single elliptical galaxy, something astronomers have already given a name, an informal name used in discussions and papers and public talks. They call it Milkomeda, or sometimes Milkdromeda, the portmanteau of the two galaxies that will no longer exist separately, folded together into something new, something vast and settled and round, without the sweeping spiral arms of either parent. A large, quiet, ancient-looking galaxy, holding in its stars the combined history of two separate island universes that crossed the void and became one. But we are getting ahead of ourselves. All of that is billions of years away. For now, Andromeda is still 2.5 million light-years distant, still approaching at 110 kilometers per second, still looking from our vantage point, perfectly still. The approach.
The universe does not send signals ahead of its great events. It does not mark the occasion. There is no alarm, no tremor, no sign visible to any eye. The universe does not announce its transformations. It simply performs them, slowly, without ceremony, over timescales that outlast everything familiar. A galaxy falling toward another galaxy across 2.5 million light-years of empty space is not an event you can watch happen. It is a state you can observe and a future you can calculate. You can hold the numbers in your mind, trace the arc of the trajectory, imagine the endpoint. You can know, with as much certainty as physics allows, what is coming. But you cannot hurry it. You cannot slow it. You can only understand it. And in understanding it, feel something that is not quite fear and not quite wonder, but lives in the neighborhood of both. Andromeda is falling toward us through the dark. It has been falling for longer than our species has existed. It will continue falling long after everything we have ever made or loved or wondered about has dissolved back into the elements from which it came. And somewhere in the unimaginable distance of the future, it will arrive. We will be here, changed almost beyond recognition, but here. The atoms that make up your body right now will still exist. Rearranged, redistributed, scattered by billions of...
The universe persists, and the slow, gravitational, inevitable fall of one great spiral of stars toward another will reach its conclusion. There is something quietly humbling about knowing this. We look at the night sky,
and we feel its stillness. We feel its permanence. And underneath that stillness, underneath what looks like a fixed and eternal arrangement, the machinery of gravity is running, patiently, without pause, drawing two vast systems of stars toward each other across a distance that swallows every human measure of time and space. The machinery has been running for billions of years. It will run for billions more. The two will meet, and the sky above whatever world remains will never be the same again.
It begins slowly, almost imperceptibly slowly. The way a tide comes in at night, while you are sleeping, while you are dreaming of something else entirely. You would not know anything had changed. You would not feel anything shift. The water simply rises inch by inch over hours, until at some point you wake and everything is different. There is no explosion at the beginning, no wall of fire rolling across the heavens, no sound, and in space, of course, there is never sound. But even the concept of sound does not apply here. Sound requires pressure, requires a medium dense enough to carry a wave. The space between galaxies is too empty even for that, too empty for almost anything. What happens instead is gravity, patient and invisible and absolutely certain of itself, the way gravity always is. Pulling, drawing, bending the paths of things that cannot resist it. Two galaxies are touching now, but not in the way that hands touch, not in the way that any two solid objects meet and recoil from each other. There is no impact in the way we usually picture impact, no crumpling of surfaces, no shockwave you could stand behind and feel through your feet. What touches, first, is influence. The gravity of Andromeda is reaching into the outer edges of the Milky Way, beginning to press against one another in slow geological motion. Think of it like this. Imagine two enormous clouds of mist drifting toward each other across a wide, flat field at dawn. You are watching from a hillside. The clouds are soft at their edges, diffuse. Hard to say exactly where one ends and the open air begins. From your hillside you watch them approach. You wonder what happens when they meet, whether they crash, whether there is a collision, and then they reach each other, and they simply pass through, swirling, mixing, tendrils of each curling through the other. Not a crash, something stranger, something quieter and more intimate than a crash. Two systems of mist becoming, temporarily, one complex, intermingled thing. This is closer to what happens when galaxies collide. Because galaxies, for all their grandeur, for all their hundreds of billions of stars, for all the awe they inspire in us, when we look at their images, galaxies are mostly empty space. Almost entirely empty space. Unimaginably, almost insultingly empty. Consider the nearest star to our own sun. It is called Proxima Centauri. It sits roughly 4 light-years away. 4 light-years. Now hold that in your mind. In a galaxy, stars are separated by distances like this on average. Sometimes more, occasionally, somewhat less, near the dense center. But throughout the vast majority of each galaxy's volume, the space between stars is colossal. There is no crowding in any human sense of the word. Even when two galaxies are fully passing through each other, even when hundreds of billions of stars from one system are interpenetrating with hundreds of billions of stars from another, the odds that any two individual stars will physically collide are extraordinarily small. Almost zero. You can work out the probability roughly. Take a star like the Sun, a ball of gas about 1.5 million kilometers across,
Place it 4 light-years from the next star. Now compress all the stars of the Milky Way and Andromeda into the same volume and let them pass through each other. The ratio of the size of a star to the average distance between stars is roughly equivalent to the ratio of a grain of sand to the distance between cities. 2 handfuls of sand thrown through each other across a city. How many grains would collide? Almost none. The stars pass like ships in a fog so thick you cannot see.
You drift through the encounter. Your path changed. Your speed altered. Your ultimate destination rewritten by the encounter. But your body intact, unscathed. This is one of the quieter truths about galactic collisions. From a human perspective, we hear the word collision, and we imagine catastrophe. We imagine destruction. We imagine something ending violently, something coming apart, something being devoured. But for individual stars, for the billions of suns caught inside this vast gravitational dance, the collision changes almost nothing at the most intimate scale. The stars themselves are untouched. They are moved. They are redirected. Their paths through space are bent and stretched and thrown into new trajectories, sometimes dramatically new trajectories. But they are not broken. Not physically, not structurally, not in the sense of one thing smashing another. What does collide, though? What crashes with genuine, spectacular, creatively explosive consequence is something else entirely. The gas. Between the stars, in both the Milky Way and Andromeda, vast clouds of hydrogen and helium drift through space. Nebulae, star-forming regions. Gas clouds, while very diffuse by terrestrial standards, are dense enough to interact with each other in ways that stars, with all their vast separating distances, cannot. When a cloud of gas moving at hundreds of kilometers per second meets another cloud moving at hundreds of kilometers per second in a different direction, the collision is real. The gas is compressed, heated, shocked into temperatures and densities it has not had in billions of years. And in that compressed, heated, shocked material, something extraordinary begins. Gravity takes hold. Pockets of gas that were too diffuse to collapse on their own, too spread out, too supported by their own internal pressure, are suddenly dense enough, suddenly compressed enough that gravity can win the argument. And so they fall inward, these pockets of gas. They spin, conserving angular momentum, the way water spins as it drains. They heat. They grow denser still. And eventually, at the center of each collapsing pocket, a new star ignites. Not through any special magic, through the same physics that made the sun, the same physics that has been making stars since the universe was young. Not one star, not 10, thousands, tens of thousands.
A collision that does not destroy but generates. A meeting that results not in fewer things but in more. We can see this process happening in other galaxies right now, today, as we point our telescopes at the sky. The antennae galaxies, 2 spiral galaxies caught in the early stages of a collision, about 65 million light-years from Earth, are alive with starburst activity. Images show brilliant clusters of newborn stars, some only a few million years old, scattered across the bridge of gas connecting the 2 systems. Pink clouds glow with the light of embedded hot stars, ionizing the hydrogen around them. Blue arcs trace the paths of young star clusters. It is beautiful. Overwhelmingly beautiful, in a way that images alone do not quite capture. violent and beautiful simultaneously, happening on timescales so slow that to us it appears frozen. Like a photograph of a fire, like a river caught in ice, like something alive held still. When the Milky Way and Andromeda begin their merger, something similar will unfold in our own galactic neighborhood. The gas clouds of both galaxies, compressed by the encounter, will spawn enormous bursts of star formation. The galaxy will fill, in those regions of active collision, with new lights. Newly formed stars.
Then they collapse and explode. Supernovae scattered across the merging system like brief, brilliant punctuation marks. Each supernova scatters the heavier elements its progenitor star forged: oxygen, carbon, iron, silicon, all the building blocks of future planets, and, eventually, of life, back into the surrounding gas. This enriched material will feed the next generation of stars and the next. Creation from collision. There is something worth sitting with in that, worth letting rest in the mind for a moment. Think about what that means, for a moment. The act of collision, the meeting of gas clouds at hundreds of kilometers per second, does not destroy the gas. It reorganizes it. It compresses it past a threshold that gravity then exploits. The same material that was drifting through the dark, too diffused to do anything interesting, is suddenly dense enough to become something. A star. A source of light and heat, and, eventually, the heavier elements that every planet is made of. The violence is not an ending. It is a catalyst. Meanwhile, something else is happening. On a scale even larger than the starburst regions, on a scale that encompasses both entire galaxies. The shapes are changing. Gravity is sculpting them.
This difference in gravitational pull, what physicists call a tidal force, acts on the galaxy the way the moon's gravity acts on Earth's oceans. It stretches. It elongates. It pulls material off the outer edges. These pulled-off streams of stars and gas are called tidal tails. Long, curving arcs of material, sometimes tens of thousands of light-years in length, swept out of the main body of each galaxy by the gravitational interaction. They trail behind the galaxies as they pass. They curve. They arch. In images of colliding galaxy pairs, these tidal tails look like the arms of something enormous reaching out, something feeling its way through the dark. Drawn out into new paths they would never have followed on their own. There is a strange grace in tidal tails. In images of colliding galaxies, they are often the most visually striking feature, not the bright cores, not the starburst regions, but those long, curving, delicate arcs of stars extending outward from the main bodies. They look fragile. They look like something drawn by hand, something made deliberately. The universe composing a shape that a human eye finds beautiful. But they are not drawn deliberately. They are the inevitable result of gravity acting on a system that is not quite in equilibrium. Stars on the far edges, loosely held, pulled just slightly more from one side than another over millions of years, until the asymmetry accumulates into something visible. Structure emerging from imbalance. Beauty from the mathematics of force. And through all of this, through the gas collisions and the starburst eruptions, and the long, slow unfurling of tidal tails, two things at the center of everything are beginning a dance of their own. A slower dance. A dance that will outlast everything else. At the heart of the Milky Way sits a supermassive black hole. Its name is Sagittarius A star.
A density so extreme it bends space-time around itself into a one-way door that nothing can exit. At the heart of Andromeda sits an even more massive one. Roughly 100 million solar masses. Perhaps more. The exact measurement carries uncertainty. A darkness so intense that even light, the fastest thing in the universe, cannot escape from its vicinity once it crosses the boundary. As the two galaxies begin to merge, these two central black holes cannot collide immediately. They are, at first, still separated by enormous distances. Each sits within its own galactic nucleus, its own dense cluster of surrounding stars and gas. But the merger process will, over billions of years, draw them closer. The stars and gas of both galaxies, losing orbital energy through gravitational interactions with each other, will gradually sink inward toward the emerging combined galactic center. The two black holes, dragged along with their surrounding clusters of stars, will spiral closer. They will form a binary black hole system. Two immense gravitational engines orbiting each other. As they orbit, they will radiate gravitational waves.
And there is an interesting difficulty called the final parsec problem, a question about whether the two black holes can shed enough energy at very close separations to actually merge, or whether they get stuck at a particular distance. Astronomers believe they do eventually merge. The gravitational waves they emit in their final inspiral would be detectable, in principle, by future gravitational wave observatories capable of sensing the ultra-low frequencies involved, a signal from the heart of the new combined galaxy. A last announcement: gravitational waves are unlike any other form of energy the universe produces. They are not light. They are not sound. They are distortions of space itself, the fabric of reality rippling outward, the way the surface of a pond ripples when you drop a stone into it. We detected gravitational waves from merging black holes for the first time in 2015. The signal lasted less than a second. The black holes involved were each only a few tens of solar masses. The black holes at the centers of the Milky Way and Andromeda are millions to hundreds of millions of times more massive. Their merger would produce gravitational waves of a frequency so low, so deep, that they would ripple through space for years.
After that merger, a single supermassive black hole sits at the center. Its mass the combined legacy of both. A quiet, dark engine at the heart of something genuinely new. But that final convergence is far ahead of where we are now. For now, the galaxies are only just beginning to touch. The outer edges. The faintest spiraling arms. The first gas clouds meeting their counterparts from across 2.5 million light-years. The first generation of new stars, born from that first collision of gas, forming in the dark. Blue, bright, brief. Blazing for a few million years and then gone, leaving their gifts of heavier elements behind. The rest of the dance has barely started.
Close your eyes for a moment. Or don't. Just let your gaze go soft. Let the particulars of wherever you are right now, the ceiling, the window, the shapes of furniture in the dark, let them go vague at the edges. Imagine you are standing on a planet, an ordinary planet, orbiting an ordinary star, somewhere inside one of these two galaxies. The planet has a surface, an atmosphere. Nights cool, and still enough to stand outside in and look up for a long time without discomfort. The sky above you is full of stars, some faint, some bright, a band of light stretching from one side of the horizon to the other. The accumulated overlapping glow of hundreds of billions of stars in your galaxy, seen edge on from your position inside it. A river of light, ancient, quiet, permanent, seeming. And somewhere in the sky, if you know where to look, a small smudge, barely visible without patience. Barely visible without truly dark skies and eyes that have fully adjusted to the night. Easy to miss. Easy to mistake for a bit of cloud or a flaw in your vision.
It is one of the most distant things the human eye can detect without instruments. 2.5 million light-years away, its light traveling through space for 2.5 million years before arriving at your retina. And yet, it covers a region of sky about 6 times the width of the full moon. We cannot see most of it, because the outer regions are too faint for our eyes, and even for most telescopes, without long exposures. The bright core is what we catch, a soft, oval blur. Ancient light. Now let time move forward. Let it flow the way time in geological or astronomical contexts flows, not in seconds or years, but in surges, in epochs, in the slow accumulation of millions of years laid one upon another like layers of sediment. 100 million years from now, that smudge in the sky has grown, not dramatically, not yet, but it is visibly larger. The core of Andromeda burns brighter, covering more sky. The outer arms, still faint, have drawn close enough that patient observation in dark conditions might begin to trace them. The two galaxies have been falling toward each other. This entire
The smudge is becoming something. By the time the two galaxies make their first close approach, somewhere in the range of 3 to 4 billion years from now, depending on the details of the encounter that computer simulations continue to refine, the sky, as seen from any planet inside either galaxy, has been transformed completely. Not incrementally transformed, not slightly changed. Transformed. Andromeda does not look like a smudge anymore. It does not look like anything our current night sky has prepared us for. We have no reference from our present experience, no analogy from what we can currently see above us on even the finest night. It spans the sky, not like a band, not like a stripe. Like a structure, vast and luminous and internally complex, irregular now because the tidal interactions have been reshaping both galaxies for millions of years. Long sweeping tidal tails curve away from the main concentration of light. A nucleus blazing, concentrated and fierce. Regions of blue-white light where new stars are erupting into existence by the millions. Darker patches where the gas is thick and the light behind it is absorbed. Pink-tinged nebulae glowing with the energy of embedded young stars. It fills a quarter of the entire sky, perhaps more, and yet it is still recognizably.
From that observer's vantage point,
Wherever they happen to be within the gravitational chaos of the merging system, the familiar star patterns of the sky are already gone. The constellations, those slow-changing arrangements that have guided every human civilization that ever existed, that have served as calendar and compass and mythology since before written language, they are gone. The stars have moved, not as they move now, imperceptibly across millennia, requiring thousands of years for a constellation to drift noticeably out of shape. During the merger, stars are being flung into new orbits. Stars that were in the thin disk of the Milky Way are being pulled up out of that disk, into new, more elongated, more chaotic paths through three-dimensional space. Stars from Andromeda are appearing in regions of sky where no Andromeda stars have ever appeared in the history of our galaxy. The sky is being reshuffled, the deck scattered, the long stable patterns dissolved and redrawn. Any constellation you might name, Orion, with his belt and his sword, and the great Orion Nebula glowing faintly in the night. Ursa Major, the Great Bear, whose 7 brightest stars make the shape familiar to children on every continent. Scorpius, arching low along the summer horizon, its heart, the red star Antares. The southern.
They merely appear to be from where we stand. Move your vantage point and the patterns dissolve. Move it by enough and entirely new patterns appear. The merger moves every vantage point by enormous amounts. Over billions of years. But the loss of familiar star patterns is, in some ways, the smallest of the changes, the easiest to name, the most concrete. What replaces them is harder to describe. A sky that is never truly dark, not fully dark, not anywhere near what we experience on the finest moonless night far from any city light. Because the starburst activity of the merging galaxies means there are always, in various parts of the sky, concentrations of brilliant young stars, clusters blazing with a collective light that has no equivalent in our current era. Nebulae, glowing with the energy of embedded young stars. Supernova remnants, expanding in slow, radiant shells that cover degrees of sky. And during the period when the 2 galactic nuclei are still separate, still distinct, visible simultaneously in the sky from the right vantage point, 2 concentrated regions of light, brighter than anything else in the sky, moving relative to each other over the centuries and millennia.
The first close approach does not mean the final merger. This point matters. It is easy to think of the collision as a single event. The galaxies meet. The galaxies become one. But that is not how gravity works over these distances. The first close approach ends with the 2 galaxies swinging past each other, each galaxy's gravity slowing the other, but not enough, not yet, to prevent them from continuing outward for some distance. Like 2 pendulums that swing toward each other, touch, and swing away. Like 2 massive ships whose wakes push against each other as they pass, distorting each other's surfaces, but each continuing on its own course for a while after the encounter. After the first pass, the galaxies partially separate, not as far apart as they were before. They will never be as far apart as they were before. But they move apart. The sky, from that hypothetical observer, shows the bright presence of the other galaxy beginning to shrink somewhat. The acute chaos of the first encounter settling, very slowly, into a new configuration. But they are bound. Gravity does not release them. They are not leaving each other. They are falling back. A second approach begins. Perhaps something like 1 billion years after the first, or less. The timing depends on the details of the encounter. A second pass.
The gravitational distortion of both systems more severe.
The structures that existed at the beginning of this process, the organized spiral arms, the thin rotating disks, these are increasingly unrecognizable. The new system does not look like two spirals passing through each other anymore. It is beginning to look like something else. Something more chaotic, more three-dimensional, more spherical. Something that is not yet one thing, but is no longer two. Then a partial separation again. Then a third approach. This is the rhythm of the merger. Not a single collision, but a gravitationally inevitable series of approaches and partial retreats. Each approach more entangled than the last. Each retreat shorter, less complete. Computer simulations consistently show this pattern. 2 or 3 major passages before the two galaxies cease to have separate identities at all. Before the two nuclei, dragged together through energy losses in the surrounding stellar populations, finally converge into one. Before the sky stops resolving into two things and becomes undeniably one. The total duration of this process, from first contact to final coalescence of the nuclei, spans perhaps 2 billion years.
And the universe is not on a human timescale. The universe has been here for almost 14 billion years. It expects to be here for far, far longer than that. On the universe's timeline, the Andromeda merger occupies what amounts to a relatively brief episode. A season in a very long story. What does the observer see toward the end? During the final convergence of the two nuclei, the sky no longer has a dark band crossing it. No thin river of the Milky Way arcing overhead. The material of both galaxies has been redistributed, stirred and mixed and flung, and pulled into a much more spherical, much less organized arrangement. The thin rotating disk that was the Milky Way, that gave rise to our galaxy's distinctive shape, is gone. Andromeda's disk is gone. What remains is an elliptical galaxy, rounder, less structured, rotating more slowly and less coherently than either of its progenitors. This is actually the expected end state. When two large spiral galaxies merge, the result is typically an elliptical galaxy. We can see this in the universe around us.
The sky from inside the new elliptical galaxy is different in a fundamental way from the sky inside either spiral progenitor. The band of the Milky Way was a product of our position inside a thin disk. We looked along the plane of the disk and saw the accumulated light of billions of stars. In an elliptical galaxy, there is no such thin plane. Stars orbit in all directions. The sky is more uniformly populated in all directions, though denser toward the galactic center. From inside the new galaxy, the center will be visible as a concentrated glow in one direction of the sky. Depending on orbital position, that glow could be subtle or blazing. Whatever sky the new galaxy provides, however unfamiliar, however stripped of every pattern any human eye has ever learned, it will be, for any being inside it, simply the sky. The only sky they know, the sky they were born under, the sky they will tell stories about, the sky that is home. We can almost imagine it. Almost. A culture of beings, somewhere in that merged galaxy, who look up at their blazing complex sky and find in it the same things we find in ours. Stories, navigation, a sense of scale, a reminder that they are small and
The merger would be so far in their past, billions of years past, that it would belong to a prehistory their instruments might just barely be able to reconstruct. They might look at the structure of their galaxy and wonder how it got its shape. Elliptical. Round. Not like the flat spirals they would observe in other galaxies nearby. And maybe their astronomers would figure it out. Would trace the stellar populations, measure the orbital distributions, find the chemical gradients left by the mixing of two different galactic histories. Would deduce, from the evidence in the stars themselves, that their galaxy was once two things. That it became one through a process measured in billions of years. That what they live inside is the product of a collision so slow it cannot be called a crash, only a meeting, a confluence, a slow becoming.
Let us come back from those billion-year views of the sky rewriting itself, back from the imagined observer standing on a nameless planet watching two galactic cores drift toward their merger. Let us talk about something closer. Our own sun, our own small, rocky, ocean-covered world. Because everything we have described, the tidal tails, the starburst regions, the long drawn-out series of galactic passes, the eventual convergence of two nuclei into one. All of this is happening around the solar system. Not to it. Around it. And the question of what happens to us, to our sun, to the Earth, to this particular modest corner of the Milky Way, is one that deserves its own careful, unhurried attention. Let us start with where we are. The sun sits roughly 26,000 light-years from the center of the Milky Way. Not at the center, where stars are packed more densely and the supermassive black hole holds court. Not at the outermost edge, where the galaxy's gravitational grip is weakest. Somewhere in the middle distance. In one of the spiral arms. The Orion arm, sometimes called the local arm, orbiting the galactic center at a speed of about 220 kilometers per second. No reason we would be at the edge. The probability of being in the middle is simply higher, because the middle is where most of the volume is. And so, here we are. This is where we are when Andromeda arrives. The stars most vulnerable to being dramatically scattered during a galactic merger are the ones in the outer regions of each galaxy. The loosely bound stars at the far edges, where the galactic gravitational field is weakest and the tidal forces from the approaching galaxy are most able to strip them away into tidal tails, into intergalactic space. The sun, sitting in the middle reaches of the Milky Way, is more tightly bound to the galactic center than those outer stars are. Not immune to disruption, but significantly less likely to be ejected into intergalactic space than a star on the galaxy's periphery. Computer simulations of the Milky Way and Andromeda merger, and there have been many, run by astronomers at various institutions, with various assumptions about the initial conditions, consistently suggest something that may seem counterintuitive at first. The most likely fate of our solar system is not destruction, not capture by Andromeda, not complete ejection into the darkness between galaxies. The most likely fate is relocation. Relocation to a different orbit within
The solar system, intact as a gravitationally bound system, moved to a new position, the way furniture might be rearranged in a room. Still furniture, still itself, just elsewhere. Some simulations place the probability of the sun being flung to a significantly larger orbit, into the outer reaches or halo of the new combined galaxy, at somewhere around 10%. Perhaps a bit more, perhaps a bit less, depending on the initial conditions assumed.
Some simulations show it staying at a roughly comparable distance from the combined galactic center as it currently orbits from the Milky Way's center. Some show it moving inward. None of the likely outcomes involve the solar system itself coming apart. A change in orbital radius around a galaxy is not like crashing into something. The stars are too spread out. The space between them is too vast. Moving from one region of a galaxy to another, even dramatically, even over a relatively short time scale by cosmic standards, does not mean encountering anything. It means a different view, different neighboring stars, different
According to the physics of stellar evolution that was set in motion when the Sun first formed, 4.5 billion years ago. The Sun is 4.5 billion years old right now. In roughly 5 billion more years, close to the same general time frame as the Andromeda collision, the Sun will have consumed most of the hydrogen fuel at its core. Stars are powered by nuclear fusion. Hydrogen nuclei colliding at tremendous temperatures and pressures, fusing together to form helium, releasing energy in the process. This energy, this outward pressure from the nuclear reactions at the core, is what holds a star up against its own gravity. What keeps it from collapsing under its own weight. 4.5 billion years from now, after 4.5 billion more years of fusing hydrogen, the core's hydrogen supply will be running low. And when that supply runs low, the balance shifts. The core contracts under gravity. The outer layers, responding to the increased energy output from the shell of hydrogen fusion that develops around the contracting core, expand. The Sun grows larger. Substantially larger. Over millions of years, it expands outward, becoming what astronomers call a red giant. Its surface temperature drops as the outer layers thin and spread, making the Sun appear redder. Perhaps somewhat more. The details of exactly how large it gets depend on the specifics of the mass loss during the red giant phase, which is uncertain. By the time the Andromeda collision is underway in earnest, by the time the merging galaxies are beginning their second or third pass, by the time the night sky is being actively reshaped by the encounter, our Sun will be old, not necessarily at the end of its red giant phase, but well into the later stages of its evolution. Swollen beyond anything it resembles today. Redder. Cooler at its surface. Brighter in total energy output. And as it swells, it will change the conditions for everything that orbits it, including the Earth. Long before the Andromeda collision fully unfolds, the Sun's steadily increasing luminosity will have already begun to alter Earth. The Sun grows roughly 10% brighter every billion years, even without the dramatic red giant expansion, simply as a natural consequence of the slow changes in its core composition as helium accumulates. A billion years from now, which is a quarter of the time remaining before the galactic collision becomes dramatic, the Sun will be hot enough that Earth's oceans will begin to be lost. Not suddenly, not all at once, but water vapor will rise more readily into the upper atmosphere, where ultraviolet radiation breaks the water molecules apart, and the hydrogen.
2 billion years from now. 3. By the time the galactic merger is in full swing, Earth's surface as we know it, the oceans, the biological communities, the atmospheric composition, will have changed beyond any easy recognition. Whether life persists, in what form, in what locations, is a question we cannot answer with certainty. Life on Earth has survived asteroid impacts that vaporize the upper atmosphere, volcanic eruptions that blanketed the planet in darkness for hundreds of thousands of years, glaciations so complete that ice may have reached the equator. Life is stubborn. Life finds edges. But the specific conditions that make complex surface life possible as we know it, liquid water in abundance, moderate temperatures, a specific range of atmospheric composition, these will not persist for billions more years unchanged. And yet, the solar system itself endures. The Earth does not fall into the sun when it becomes a red giant. Not immediately, not certainly. The expanding sun will envelop Mercury and likely Venus. Whether it reaches Earth's orbit is a genuine scientific question.
Even in that case, the rocky body of Earth, its iron core, its silicate mantle, is not vaporized. It is scorched, stripped, changed. And then, when the sun finishes its red giant phase and exhales its outer layers into space, as a planetary nebula, a beautiful expanding shell of gas, lit by the newly exposed hot core, it shrinks to a white dwarf, a small, dense, slowly cooling remnant, about the size of Earth, but containing most of the sun's remaining mass, an ember. And if Earth survives this process, it continues to orbit that ember, in the cold, in the quiet. An ancient, bare, geologically frozen world, circling a slowly dimming white dwarf. This is the solar system's fate, regardless of the Andromeda collision. The merger does not write this story. It does not change the essential shape of what happens to the sun and its family. The sun's aging is an internal drama, written into the physics of nuclear fusion 4.5 billion years ago. The Andromeda collision is an external event, a vast gravitational ballet playing out above the solar system, while the sun continues on its own.
And the stars of both galaxies, passing through each other, swept into tidal tails, flung into new orbits. These stars are not physically destroyed by the encounter, not broken, not converted into something other than stars. They are moved. They are redirected. Their neighborhoods change. Their views of the sky change. But a star that enters the merger as a stable, fusing, ordinary star will exit the merger, billions of years later, as a star that has aged by billions of years, just as it would have, whether the merger happened or not. This is the gentle truth at the center of the collision. Collision does not mean destruction, not at the scale of individual stars. It means change. It means redistribution. It means that something that was in one place will be in another, and the sky above it will be different, and the neighborhood of stars around it will be different, and the galaxy it belongs to will be different. But the thing itself, the star, the solar system, the orbiting planets, continues. Out there in the new, merged galaxy, the combined elliptical system that inherits everything that was the Milky Way,
And in a wide, cold orbit around that white dwarf, the Earth will circle. Quiet, made of atoms forged in stars that lived and died before the sun was born. Carbon, oxygen, iron, silicon, all the elements that make a rocky world, all the elements that make a living thing, traveling through space in the remnants of those ancient supernovae, gathered eventually into the cloud that became the solar system, gathered further into the planet we stand on. These atoms have already survived billions of years. They have already been through the interiors of stars. They have already been scattered into space and reassembled.
A galactic collision does not end them. It only moves them. And somewhere in the new galaxy, orbiting its new galactic center on whatever trajectory the merger assigned it, the solar system continues its quiet, ancient circuit.
The organization. It does not reach down to the scale of a single planetary system and undo it. Gravity at the galactic scale is, in its effect on individual stars, more like a gentle redirection than a force of destruction. A long, slow hand rearranging pieces on an enormous board. Moving things, not breaking them. And at the end of the merger, on the far side of billions of years, something new. A galaxy that is neither the Milky Way nor Andromeda. Something formed from both of them together. Something that did not exist before this encounter began. The stars of our galaxy and the stars of Andromeda, 1 trillion or so of them, combined, settling into new orbits around a shared center. The two supermassive black holes having slowly spiraled together. The wild bursts of star formation having faded as the gas is consumed. The chaotic, luminous sky of the merger gradually stilling into something calmer. Something older looking. Something like the quiet after a very long storm. Not an
Something new is settling, not arriving, not crashing, just settling, the way dust settles after a long disturbance, the way a disturbed pond finds its level again, ring by ring, until the surface goes still. 6 billion years have passed since the first close encounter. 6 billion years since that great curving approach, that long arc of mutual falling. The two galaxies have pulled through each other, separated, returned, and now, finally, irreversibly, they have become one thing, not two things pressed together. One. And the name that astronomers have given to this one thing, this merged result of the Milky Way and Andromeda, is a name that carries something almost tender in it, a blended word, a word stitched together from both parents. Milkdromeda. Some call it Milkomeda. The syllables are slightly different, but the feeling is the same. A portmanteau of two galaxies, the way you might blend the names of two people who decided to become a family. Milky Way. Andromeda. Milkdromeda. It is not a dramatic name. It is not a triumphant name. It sounds almost soft, a little awkward, the way new things often are. And that softness feels right.
The most fundamental difference between the galaxy that was and the galaxy that is. The Milky Way, for all the billions of years of its existence, wore its structure like something it was proud of. Those long sweeping arms trailing out from the center, wrapped in the blue-white light of new stars, threaded with dust and gas and the constant business of stellar birth. Andromeda had arms too. Different proportions, different tilt, a slightly different pattern, but the same essential shape, a pinwheel.
a long chaotic tangle of overlapping gravity. All of that undid the delicate orbital choreography that maintained those arms. Stars that had circled the galactic center in neat organized paths for billions of years found their orbits disrupted. Nudged inward, nudged outward. Tilted, scrambled. Think of it like this.
It is something else, something with different rules. Andromeda is an elliptical galaxy. Astronomers classify galaxies in broad shapes, and ellipticals are among the oldest, the most settled, the most structurally simple. Where spiral galaxies are disc-shaped and busy, full of gas and new stars and active star formation, elliptical galaxies are more like smooth, rounded clouds of stars. They can be nearly spherical, or stretched into a football shape, or somewhere between. They have no arms, no disk, no grand organized rotation. Their stars move in a complex three-dimensional tangle of orbits, each one slightly different from the next, averaging out into a shape that is round and featureless, and in its own way, restful. Andromeda is something like that. A large, smooth, roughly ellipsoidal collection of stars. From the outside, if you could see it from the outside, it would look like a soft glowing smear of light. Warm in color, slightly amber.
The great burst of star formation that accompanied the collision, all those new stars ignited by compressed gas clouds colliding, all those blue-white sparks in the maelstrom, consumed enormous reserves. What gas remains is thinner, more scattered, harder to assemble into the dense clumps that collapse into new stars. Star formation has slowed. In some regions it has nearly stopped. And so the galaxy ages. The hot massive blue stars that formed during and after the merger burn bright and burn fast and die, and they are not replaced at the same rate. What remains is an older population of stars, cooler, redder, longer lived. The kind of stars that measure their lives not in tens of millions of years, but in billions. Red giant stars. Orange subgiants. Yellow stars like an older, cooler version of our sun. They are not dramatic. They do not blaze. They glow with a steady warmth, a long, slow, patient light. Like embers that have been burning for so long they no longer remember what it was like to be a flame. Andromeda, seen from afar, would be amber orange. A warm, dim glow.
Our Milky Way's black hole, known as Sagittarius A star, has a mass of roughly 4 million times that of the Sun. Andromeda's central black hole is significantly more massive, somewhere between tens of millions and perhaps over 100 million solar masses. Large, patient, waiting at the heart of its galaxy for 4 billion years. When galaxies merge, their central black holes do not immediately merge. For a long time, millions, even hundreds of millions of years, they orbit each other. A slow binary dance at the center of the new galaxy, two enormous gravitational anchors circling their shared center of mass, drawing closer with each pass as they lose energy to the surrounding stars, scattering stars outward as they spiral in. Eventually, given enough time, they merge. The merger of two supermassive black holes is one of the most energetic events in the universe. It releases gravitational waves, ripples in the fabric of space-time itself, on a scale that dwarfs anything produced by the merging of stellar mass black holes. The kind of ripples that could in principle be detected across enormous distances. And then they are one. A single, larger, more massive black hole at the center of Andromeda.
What remains at the center of Andromeda is simply a very massive, very quiet gravitational anchor, not devouring much, not producing much, just sitting there, curving space-time, holding the heart of the galaxy in its grip, a center of gravity, literally and in its way, figuratively. All those stars, the hundreds of billions from the Milky Way, the hundreds of billions from Andromeda, plus the generations born during the merger, orbit this center. Their paths are complex, three-dimensional, not the tidy circles or near circles of a disk galaxy. They cross and weave in precess. The galaxy breathes in a slow, statistical way, stars oscillating through the center and back out, like fish in a spherical tank, each taking its own path, none of them following exactly the same route twice. From inside this galaxy, standing on a planet orbiting one of those stars, the sky would look different from the sky we know. Let us imagine that. Let us imagine you are somehow there.
In our current Milky Way, standing somewhere in the disk at roughly our distance from the center, the night sky shows a band of light, the galactic plane, where the combined glow of hundreds of billions of distant stars concentrates into a soft river across the darkness. Beautiful, subtle. In Andromeda, an observer might see something richer. The stars are not confined to a flat disk anymore. They surround you in 3 dimensions. Look in any direction, and the stellar density is higher than what we have today. The sky on a clear night would be brighter with background starlight. More stars visible to the naked eye. The band of the old galactic plane is gone, replaced by a more diffuse glow that fills a larger portion of the sky, denser toward the core, fading toward the edges. The center of the galaxy, seen from a location similar to where our sun currently sits, would appear as a bright concentrated region, warmer in color than what we see when we look toward Sagittarius today. More orange, more golden. The merged black hole and its surrounding population of old stars, creating a nucleus of gentle light. And the neighboring galaxies, the Magellanic Clouds, the 2 small satellite galaxies that travel with the Milky Way today, visible from the southern hemisphere as detached patches of the Milky Way.
Swallowed into the merger over the preceding billions of years, their stars scattered into the halo of Andromeda or settled into the main body. The Triangulum Galaxy, the 3rd largest member of our local group, may have been pulled in as well. The local group, over these timescales, tends toward consolidation. Smaller galaxies fall into larger ones. Satellites become parts of the main body. The neighborhood simplifies. Beyond the local group, the expansion of the universe has been doing its work. All those distant galaxy clusters and superclusters, already receding from us today, are by this point so far away that even their light takes longer to reach us than the age of the universe as we know it now. The observable universe visible from Andromeda is slightly different from the one visible from our current sun. Older, more expanded, the distant galaxies farther away in every direction, the universe more sparse, the night between the stars and clusters slightly deeper. But none of that distance touches the intimacy of being inside Milkdromeda. Inside, the galaxy is still warm, still luminous, still full of stars living their long lives in their tangled orbits.
The beauty is not in the drama. It is in the steadiness, the depth of the quiet. Milkdromeda has that kind of beauty. It has been through everything. The long spiral approach across 4 billion years, the first pass, the chaos, the burst of fire and new stars, the retreat and the return, the slow weaving together of two vast systems of stars, the black holes circling and finally becoming one. All of that is behind it now. What remains is a galaxy in its long middle age, heading eventually toward old age, not dying, not yet, but settled and slow and warm and round. Its stars will keep burning. Some will die and leave behind neutron stars or white dwarfs or small black holes, and those remnants will orbit among the living stars for far longer. The galaxy will persist, changed but real. Milkdromeda, a name stitched together from two names, a galaxy stitched together from two galaxies, something that never existed before, made from things that existed for billions of years, now continuous with both of them and identical to neither. If you are drifting somewhere near the edge of sleep now, let that image hold you for a moment. A warm amber cloud of stars, gently.
Let it be something you do not need to touch or understand or hold. Just feel the soft light of it, the warm old light of hundreds of billions of stars, very far away, very long from now, going about the quiet business of burning.
There is a particular quality to time when you look at it from very far away. Up close, time feels urgent, relentless. There are deadlines and mornings and the sound of the hour changing. There is the calendar and the pressure of all the days that have already been used, and all the days still waiting, and the feeling that none of them are quite long enough. But when you pull back far enough, time changes its nature. It becomes a landscape. You have spent this past hour or two following the story of two galaxies through billions of years. You have watched. In imagination, in the slow unfolding of these words, the long approach of Andromeda across the darkness, the gravitational pull that built across 4 billion years like a note slowly resolving, the merger, the chaos and the fire and the new stars, the settling, the smooth, warm elliptical galaxy resting in the deep future, amber and quiet. All of that has taken place inside the space of a human evening, and it is worth sitting with that for a moment before sleep takes you. The strangeness of it, the scale of it, and paradoxically, the comfort of it.
The oceans may not. The specific forms of life that fill those oceans now, including everything descended from everything alive today, those will be different, changed, unrecognizable. But the planet will be there. The star will be there. The atoms that make up everything you see around you now will still be in motion, still part of something, still participating in the universe. 4 billion years is not an empty number. It is a number that contains inside it the entire history of complex life on Earth, multicellular life, forests, seas full of fish,
the age of the dinosaurs and their 200 million years of dominance, the mammals that followed, and the long line of primates, and the very recent hairless upright ones who learned to name things. All of that, the entire pageant of life's evolution, everything that ever lived and died and changed and gave rise to the next thing, that is what fits inside 4 billion years. And that is how much time remains before the first touch. It is almost impossible to hold that in the mind. The mind was not built for it. We are creatures of seasons, of lifetimes, of decades at the most. We can manage a century with some effort. 1,000 years stretches us. 1,000,000 years makes the mind go quiet and slightly blank, like trying to see something too large to fit in a single gaze. 4 billion years does not fit.
And yet it exists. It is real. It is out there ahead of us as surely as tomorrow morning is ahead of us, just unimaginably, inhumanly far. And the strange thing, the thing that might feel like a gift if you let it, is that you do not have to carry any of it, not 1 year of those 4 billion, not 1 century of the merger, not 1 slow orbit around the new combined galaxy. It is all going to happen without you. This is not a sad thought, or at least it does not have to be. There is a particular kind of relief that comes from understanding scale, from allowing the enormous to be enormous and letting yourself be small inside it, not diminished, but released. You do not have to be the reason everything happens. You do not have to hold the galaxies in their courses. They were doing this long before you arrived, and they will keep doing it long after you are gone, and your presence here, brief and warm and particular as it is one small true thing inside a much larger story that you did not choose and cannot control and do not need to carry. Right now, at this moment, while you are lying
in the actual sky above you, 2.5 million light years away, behind the ceiling and the clouds and the blue of the daytime atmosphere or the dark of the night, the real Andromeda, moving, closing the distance. It has been moving toward us for billions of years already, long before there were any eyes to watch it, long before there was a planet to watch it from, and right now, in this precise moment, it is closer than it has ever been before, and in the next moment, closer still. Each second, each breath you take, the gap narrows by some small fraction. You are living inside the slow accumulation of approach, and you are breathing, and you are warm, and the movement of those hundreds of billions of stars does not press on your chest at all. Astronomers have a concept called deep time. It refers to the vast geological and cosmic timescales that ordinary human experience cannot encompass. The age of the universe, nearly 14 billion years. The age of the Earth, 4.5 billion years. The future lifetime of the Sun, another 5 billion years.
The physicist Richard Feynman once described the feeling of looking up at the night sky and knowing what the stars were, really knowing it, as something that only added to the beauty. That knowing the names and distances and natures of things does not reduce the wonder, it deepens it. There is something like that here. Knowing that Andromeda is real and approaching, and that the approach will take 4 billion years, and that the merger will last another 2 billion, and that what comes out the other side will be a warm old elliptical galaxy called Milkdromeda, glowing quietly in a universe much older than ours. Knowing all of that does not make the sky above you smaller. It makes it larger. It makes this particular moment, you, here, breathing, warm, quiet, feel like something that is happening inside a story so vast and so old that its slowness is itself a kind of peace. You are a brief, warm brightness inside deep time. A match struck in a vast dark room, burning clearly and truly for a moment, and then going out, and the darkness coming back, different for having held that light even briefly. And the room does not mourn the match. The room is too large for mourning, too patient, too full of other lights coming and going in their own time. What the room does, what the universe does, is simply continue.
Galaxies fall together and come apart and fall together again. Stars are born in clouds of gas and burn for millions or billions of years and collapse. And their material drifts back into the galaxy and becomes the raw material of the next generation. Black holes sit at the centers of things, patient and enormous. Clusters of galaxies move away from each other on the expansion of space-time, each cluster its own island universe now, separating from all the others over trillions of years. The universe does not hurry. It does not worry. It simply proceeds through its own enormous logic, one step at a time, each step taking millions or billions of years, each step as inevitable as the next. And right now you are one small warm part of it. Your atoms, the carbon in your cells, the oxygen in your blood, the iron that gives that blood its color. All of those atoms were made inside stars. Older stars than our sun, stars that lived their lives and died before the solar system existed, and scattered their heavy elements into the galaxy. And those elements eventually became part of the nebula that collapsed into the sun and its planets, and eventually into the chemistry of a living world, and eventually into you. You are made of stars that are already gone.
You are a temporary arrangement of ancient material, thinking and feeling for a little while in the middle of a vast dark space that mostly does not think or feel. That is remarkable, not sad. Remarkable. The astronomer Carl Sagan described humans as the way the cosmos knows itself. The universe through us looks at itself. Through our eyes, Andromeda is observed. Through our mathematics, its approach is calculated. Through our imagination, its future is pictured. Through our voices, its story is told on quiet evenings to people who are trying to rest. The universe does not need to know itself. It would proceed just fine without the knowing. But somehow, in this particular corner, for this particular moment, it does. Through you. Through all of us. Think of your own life for a moment. Not the parts that feel large and unfinished. Not the goals or the worries or the things that did not go the way you hoped. Just the small, specific texture of it. The way a particular room smells in the morning. The sound of a voice you know well saying something ordinary. The specific weight of a blanket. The color of light through a window you have looked through many times. These small things are real. They are happening inside the same universe where Andromeda is falling toward us. They occupy the same space-time.
None of them will last. The room will eventually not exist. The voice will eventually fall silent. The window will be gone. In billions of years, even the planet will be gone. And in trillions of years, even the stars will mostly be gone. And the universe will be old and cold and spread very thin. But that is trillions of years away. And between now and then, an enormous amount of warmth, an enormous amount of light, an enormous amount of exactly this, small, particular, real moments, lived by brief, warm creatures in their brief, warm lives, inside a cosmos so large it cannot be imagined. You do not have to be large. You are allowed to be small. You are allowed to be temporary.
You are allowed to be a creature who breathes and sleeps and wakes and spends their days mostly in the middle-scale world of rooms and conversations and meals. That is not a failure to be cosmic. That is what being alive in the cosmos actually looks like from the inside. The merger of the Milky Way and Andromeda will not be experienced by anyone alive in 1,000,000 years. The time between now and the first touch is longer than the time since the first multicellular animal crawled across the floor of a shallow sea on a young Earth. We will not be there, and somehow that is all right, because we are here.
Right now, in this particular sliver of deep time, in this particular configuration of the universe where the Milky Way is still a spiral, and Andromeda is still a separate thing, and the sun is still middle-aged, and the earth still has oceans, and the oceans still have life, and some of that life is warm-blooded and curious, and built houses, and lit fires, and looked up at the sky, and wondered what was out there. We are in the wondering era, the looking up era, the era of fires lit against the dark. It will not last forever. Nothing lasts forever. But it is happening now, and the fact that it will not last is part of what makes it worth noticing. There is a quality of comfort in deep time that takes a moment to find, but once you find it, it does not let go easily. It is this: nothing you are carrying right now matters on a cosmic timescale. Nothing. The things that feel heavy and urgent and unresolved, they are real, and they belong to your life, and you are allowed to feel them fully. But they exist at the scale of days and years. The universe operates at the scale of billions. And in that mismatch,
You would not notice it. No instrument on Earth could detect it in real time. But it is happening. The slow accumulation of approach is happening. The gravitational attraction, building across millions of light years, is doing its quiet work, and you do not have to help. The galaxies do not need you to hold them on course. Gravity does not need oversight. The deep future of the universe is not waiting for your input. It is proceeding. It has always been proceeding. It will proceed long after everything you know is gone, and it will be doing what it does: stars and gravity and light and the long, slow dance of matter, and none of it will require anything from you. You can let all of it go. You can let the galaxies move in their own time. You can let the merger happen without you. You can let Andromeda exist in its warm amber future, full of old stars in their woven orbits, a black hole sitting quietly at the center of all of it, without needing to watch. Here is what is true right now, in this moment. You are breathing. The breath.
Your mind floated through the deep future and came back. The bed or the couch or whatever is beneath you is still there. The room around you is still there. The ceiling is still above you. Outside, the sky, whether dark or beginning to lighten, is still doing what skies do, moving, slowly brightening, or slowly deepening. The stars above you
the ones you cannot see through the ceiling and the walls, are burning with their patient, slow fire. And Andromeda is out there.
That is, in its way, extraordinary. Let the breath slow. Let the thoughts drift apart, the way stars drift apart at the edge of a galaxy. Slowly, with enormous patience, with no urgency at all. The merger is 4 billion years away. Milkdromeda is 6 or 7 billion years away. The heat death of the universe is trillions of years away. You are here now. Now is the only place you need to be. The galaxies will take care of themselves. They have been doing it for a very long time. They will keep doing it. Gravity will keep doing its quiet, patient work. Light will keep crossing the distances between things. Matter will keep finding new arrangements. The universe will keep being enormous and mostly dark and full of small, warm lights. And somewhere out there, in a future so far ahead that its very distance is a kind of mercy, 2 galaxies are becoming one. Slowly, without drama, the way all the best transformations happen, too gradually to witness, too complete to deny. And right now, tonight, you are resting at the edge of all of that. A small, still life inside an enormous moving.
They exist in the same universe as everything you have heard tonight, and they are not diminished by it. If anything, they are brighter, more particular, more real. The warmth of your own body, the sound of your own breathing, the specific feeling of this particular night, settling around you. Out in the dark, across 2.5 million light-years, Andromeda is there. It will still be there in the morning. It will still be there in 1,000 years. In 1,000,000. In 4 billion. Patient. Real. Falling toward us in its enormous slow arc. And the Milky Way is holding you right now. This whole vast spiral of 300 billion suns, turning slowly in the dark. One of those suns yours. One of those suns warming the planet under your feet. The whole system moving through space in its own long orbit around the center of the galaxy, which is itself moving, everything always moving, always in relation to everything else. And in the middle of all that motion, you are still. You are very still. Let the deep time carry what the day could not. Let the scale of it do what the mind cannot.
Just the next chapter of something that has been unfolding since before there were any eyes to watch it, and will keep unfolding long after the last light of tonight is gone. You do not have to understand it. You do not have to hold it. You only have to rest. The universe is very large. You are very small. And right now, the small warm fact of you, breathing, resting, here, is exactly right.